All right, so in order to compare the trapezoid rule and the midpoint rules, it's easier to think of these areas of these subintervals as trapezoids. Now, obviously, I've already talked about the trapezoid rule, how this essentially, you're breaking the subintervals into trapezoids because you're averaging the right and left endpoints. Okay, so, and it also ends up that you can just do the left-hand sum and the right-hand sum, average the two, and you get the trapezoid rule for that function. Now, the midpoint rule is a little less easy to see how you can make that into a trapezoid. But let's take a look at this diagram. I'm going to scroll down just a tad here. Take a look at this diagram. So in the midpoint rule, we're basically taking the value of the function at the midpoint and using that as the height of the rectangle for the area that we're calculating. But if I draw a tangent to the curve at the midpoint, okay, that's this line here, right? Oops, it's hard to draw a straight line. You can see we get these triangles, and if we look at, we have a couple of vertical angles right here. We also know that this is the midpoint, so we know that this leg is the same length as that leg. And we also know that each one of these is, we're estimating with rectangles, so this has to be a right angle. So if you look at these two triangles, the triangles are congruent, right? So because the two triangles are congruent, now, and it's by ASA, if you remember any of your high school geometry, if you have two angles and the side between it are congruent, then the two triangles are congruent. So by ASA, those triangles are congruent. And so, so when we draw this trapezoid, this area here, is above the rectangle. This area here is below the rectangle, so we're increasing the area by this by one of these triangles, and then we're decreasing it by the same amount because the triangles are congruent. So we can actually visualize the midpoint rule as being a trapezoid, where the top of the trapezoid is, or the side of the trapezoid, however you want to look at it, is a tangent line to the curve. Okay, and that makes it a little easier to compare these values for the trapezoid and the midpoint rule, because as I said before with that last example, it was hard to see whether the midpoint rule gave you an overestimate or an underestimate. But if you visualize it as a trapezoid where the side of the trapezoid is a tangent line to the curve, then you can see, if you've got something that's, in this case, you can see this curve is concave down, and you can see the error, here I can try to draw it in red, is here and here, and it's above the curve, right? So in the case of for a concave down function, you'll get an overestimate. All right, so let's take a look at example 2. In example 2, what we're doing is trying to evaluate the left, the right, and the mid and the trap rules, and determine whether these give us an underestimate, or an overestimate. Okay. So I'm going to stop because I need to draw some pictures, and I don't want to make you watch me draw pictures, and then we'll talk about this some more. All right, so in this example, we are asked we're told that we have an increasing function, okay, and we're asked which of left, right, mid, and trap are guaranteed to be an underestimate and which are guaranteed to be an overestimate. And we drew some sketches. I drew some sketches here to help explain. All right, so if you look at the left rule, when you estimate the area of a subinterval, right, you're using the left-hand data point, and if the function is increasing, then the left-hand data point is always less than the right-hand data point. So the left is going to be an underestimate. And in the case of a right in case of the right rule, right, we're using the right hand data point, which is always greater than the left hand data point for an increasing function. And so we're going to have an overestimate. Okay, and so that the error, essentially, I've shaded in what I'm considering the error, our difference between our actual function and our estimate. Okay. Now, for the midpoint rule and the trapezoid rule, it's a little different. We can't really determine whether it's an over or underestimate just based on whether the function is increasing. So I drew the function two different ways in all of these cases. One, it's increasing in concave up, and in the other one, it's increasing in concave down. And you can see that for the mid and trap, sometimes we get an underestimate, right? In this case, where it's concave up, the midpoint rule gives us an underestimate, right? Because this tangent line at the midpoint is below the curve, except for at the midpoint, of course. And in the case of where it's increasing in concave up, then that tangent line is above the curve, so we're going to end up with an overestimate. Same way with the trapezoid rule. If we take the average of the two endpoints, right, and essentially estimate the subinterval with a trapezoid, then if the function is concave up, then we have an overestimate, and if it's concave down, then we have an underestimate. Okay, so the next one is asking us, the next part of this example is asking us if the function is concave up, which of left, right, mid, and trap are guaranteed to be underestimates or overestimates. And again, we want to draw sketches. Now, based on the sketches I just drew, you can probably answer this question, but I'm going to pause here and draw my pictures, and I'll come back and we'll talk about it. All right, so I've drawn some sketches for part B. So again, we're, f of x is said to be concave up, and I drew two cases, one where it's concave up and increasing, and one where it's concave down and decreasing. So in each case, I have both of those scenarios. And you can see for left and right, whether or not it's an underestimate or lower estimate is dependent on whether it's increasing or decreasing. It's not dependent on the concavity at all. It's dependent on whether it's increasing or decreasing, which we have kind of established already in part A. Now for mid and trap, you can see the midpoint rule. If we represent the area of the interval as a trapezoid, where the end of the trapezoid is a tangent line to the curve, right? Then you can see this tangent line is always below the actual curve. And it doesn't matter whether it's concave up and increasing or concave up and decreasing. This tangent line is below the curve, and so the midpoint rule gives us an underestimate. And for the trapezoid rule, so the area is represented by a trapezoid, where the connecting these two endpoints. And so you can see that the line between the endpoints within the subinterval is always above. When it's concave up, the line is always above the actual curve. And so the trapezoid rule gives us an overestimate. Okay, so now there's one other thing I want to mention here before I stop, and that's just, okay, so now, based on our other calculations, it's looking like, the trapezoid rule and the midpoint rule give us the most accurate estimations of the integral. And now that we know this issue with, how this issue with concavity works, we can also put some bounds on our integral based on the trapezoid and the midpoint rule. So now I'm going to start with the second one first, because we just did a case where it's concave up, and we found that the midpoint rule gives us an underestimate, right? Which means that, and the trapezoid rule gives us an overestimate. So the midpoint rule will always be less than the integral, and the trapezoid rule will give us an estimate that's greater than the actual integral. Now, when it's concave down, we can actually draw a little picture of that. So it's concave down. Oops, I can't. That's why I drew these off offline. It's hard to draw. So that's concave down and decreasing, and then we could also look at a scenario where it's concave down and increasing, right? And in this case, if we look at the trapezoid rule, it's always going to be an underestimate, right? So that is the trapezoid rule, and this is essentially the difference between the area of the trapezoid and the actual area. So in this case, the trapezoid rule gives us a lower bound, and the midpoint rule gives us the upper bound. Because again, if it's concave down, let me see, I can draw these again. There's a concave down and decreasing. Oh, it's kind of, and you can see that the tangent line is above. So it's going to give us an overestimate. The same way if it's concave down and increasing, right? The tangent line is above. So the midpoint, I'm not drawing this very well, but the tangent line is above, so it's going to give us an overestimate. Here we had an underestimate for the trapezoid rule. Okay, so now we have some bounds on our integral. So the next problem, example 3, I want you to go ahead and try that on your own. Okay, it's similar to the one we just did on, I guess, example 1. So I want you guys to give this a try. So try it, and then I'll meet you for the next video.